So here we go. Welcome back. It is the first time we'll see new content since last week. We will be doing some notes today, so please have your notebooks ready, or whatever it is you use to take notes. Please have it ready. We'll be covering some new content. One thing I do want to jump into the Canvas course here real quick to start. To go over a couple things. So we'll do that first. And yeah, so here we are, we're in our course. Obviously we have all these things in here. Here's a presentation for today on the 27th. I'll upload the recordings later today once they're ready. I've added in the things you might need. We have our formula sheet and tables from the 2020 exam. Our formula sheet and tables should be pretty much the same this year. So it's got like your table A on it, formulas that will be provided when you take the AP exam, things like that. I also just added this page, that tab. It's just got a couple videos that I made from last semester showing how to use table A in a couple different ways, different types of problems. This is something that we need to know how to do, so I've added it to that, things that will be useful tab there, things that you might need. And it's been asked to kind of have something there to provide more resources. Also, one of my main projects yesterday was I went through and recorded some review free response questions. I think there's 5 questions, I believe, that I did on this video. It does take about 40 minutes, but it is meant to be kind of an overarching review of the types of problems you should be able to do after today's lesson, since today's lesson is the last lesson for chapter 6. It might be useful to look over these questions before attempting the free response questions for the chapter 6 assessment. All right, so that is now available. All right, so I've added some extra videos here. I'm gonna try to, hope maybe today, do a little bit of editing on the video to kind of tag where each problem starts in like the navigation of the video. I'm not sure how to do that, but I'm gonna try and figure it out. So there is that. And lastly, we have our multiple choice questions and then the free response question. I don't remember if I went over this with you guys. This does look slightly different than how we did the free response and self-assessment last semester. I've set it up as an assignment rather than a quiz. This is to give you multiple ways of submitting based on what you're most comfortable doing. There are 2 sections, so to say. First section is free response questions. There are 2 questions with multiple parts. The first one is random variables, probability distributions, combining random variables. Then question 2, binomial and geometric distributions. You'll know how to do this after today, hopefully. Section 2 is the self-assessment and reflection. All right, and so somewhere in your submission, you need to do both sections. This is what grade do you think your understanding deserves? Give me a reason why, and then a reflection question. Please answer that one as well. You have the option to do just a simple text entry, right? You can, if you feel savvy, you can like make a website, I don't know, use like a Google site and put all your solutions in there. You can record yourself answering the questions if you like, or you can upload a file, right? You have all those options available. Whichever one you're most comfortable using, please use. You just need to submit something with your responses. If you're uploading a file, remember that it typically will only allow you to upload 1 file. So make sure that all of your things that you want to submit are contained in that single file. Right? If you're doing your work by hand, right, on pieces of paper, and you're taking pictures of it, you can't upload separate pictures, right? So make sure that you're using like a scanning app on your phone. There's a bunch of free ones out there that will let you take pictures of multiple pages and combine it as a single file. Right? That's what we need. I need a single file with your work. Also, do keep in mind if you're doing the text entry, you can add pictures, right? You can upload images. So if you want to upload your work that way, take pictures and upload it through the text entry, that's totally fine too. Right? Whatever is easiest for you to manage, do that. All right. So those are the new options on the free response question self-assessment. I wanted to make sure and review that because I don't remember if I did with you guys. So there's that. So that's kind of a couple of things that I've added to the course and things that are a little bit different. Yeah. Is there any questions about the stuff in the course? All right. If there's anything you'd like me to add or that you'd like to see in the course, please let me know. I'm happy to make changes and make additions to make things better for you guys. All right. And with that, we're going to switch over to our presentation for section 6.3. So if you're taking notes, get those ready. Because we're going to have some new stuff. All right, there's going to be some new formulas today. All right, some new kind of like definitions, things that you're going to want to be able to reference. All right, so please be prepared for that. So here we are. We're going to start section 6.3 and get through all of it today. We have binomial and geometric random variables. All right, so we've talked about what a random variable is, right? How to use them. Now we're going into special kinds of random variables. Here we go. So for this lesson, we're going to focus on determining whether the conditions for using a binomial random variable are met. We're going to compute and interpret probabilities involving binomial distributions. We're going to calculate the mean and standard deviation of a binomial random variable and interpret these values in context. That's always going to be a thing when you find a mean, standard deviation. When you're finding special values, you're going to be asked to interpret them in context. What does it mean in the context of the question? Right? Find probabilities involving geometric random variables, and when appropriate, use the normal approximation to the binomial distribution to calculate probabilities. All right. So there we go. Again, normal approximation is coming up again. Right. So what is a binomial setting? Right. When the same chance process is repeated several times, we are often interested in whether a particular outcome does or doesn't happen on each repetition. Right. Some random variables count the number of times the outcome of interest occurs in a fixed number of repetitions. Right. They are called binomial random variables. Right. So this is important. We're considering a fixed number of trials, a fixed number of repetitions. All right. If I have a fixed number of repetitions for a trial here, then we can maybe use a binomial random variable. A binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. Right, the four conditions for a binomial setting are as follows. Right, there's four special conditions. Number one, is it binary? Right, the possible outcomes of each trial can be classified as a success or failure. Right, there's only two options. It can be a success or a failure. Must be binary. Is it independent? Trials must be independent. That is, knowing the result of one trial must not tell us anything about the result of any other trial. And this is the same definition of independence that we've seen previously. Right? So it has to be binary, has to be independent. Number, right? The number of trials n in the chance process must be fixed in advance. All right? We can't just randomly select the number of trials every time we perform the process. and success. There is the same probability P of success on each trial. This kind of ties back into independence, right? If something's not independent, then the chance of success changes based on one of the previous outcomes, right? So as long as it's independent, we should have the same probability of success on each trial. Right, so these conditions we need to know. We need to be able to check them to see if something is in a binomial setting and if it can be represented. If we can use a binomially random variable and then use binomial distribution, right? So we get the letters bins. Right? So if you want to know if something is in a binomial setting, you need to check your bins. That's kind of the little moniker we can use, right? Check your bins. All right. So can you please raise your hand if you need a moment to write stuff down? Nobody, okay. All right, so consider tossing a coin n times. Each toss gives either heads or tails. Knowing the outcome of one toss does not change the probability of an outcome of any other toss. If we define heads as a success, then P is the probability of a head and 0.5. The probability of a head is 0.5 on any toss. The number of heads in n tosses is a binomial random variable x. The probability distribution of x is called a binomial distribution. All right. The count x of successes in a binomial setting is a binomial random variable. The probability distribution of x is a binomial distribution with parameters n and p. When n is the number, where n is the number of trials of the chance process and p is the probability of a success on any one trial. Possible values of x are the whole numbers from 0 to n. Okay, so I can only have up to n number of successes. Okay. Please don't worry, we will see an example. Once again, if you need a moment to write anything down, can you please raise your hand? And if there's anything I can clarify so far, please unmute your mic and tell me or type it in the chat. Okay. So in a binomial setting, we can define a random variable, say x, as the number of successes in n independent trials. We are interested in finding the probability distribution of x. So here is an example. Each child of a particular pair of parents has probability 0.25 of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, the count x of children with type O blood is a binomial random variable with n equals 5 trials and probability 0.25 of success on each trial. In this setting, a child with type O blood is a success. Right, we'll label that S, and a child with another blood type is a failure, F. What is probability of x equaling 2? So what's the probability of the parents having 2 children, exactly 2 children with type O blood? This fits into our binomial situation here, so we can use the binomial distribution. We'll get into that momentarily. So here's one way of calculating this for a single possibility. The probability of the first 2 children having type O blood and then the next 3 not having type O blood, right? We get 0.25, 0.25, 7.75, 75, right? Probability of success 2 times probability of failure 3 times. We get 0.25 squared times 0.75 to the third, and we get a probability of about 2.6%. And that's just for the single possible outcome of the first 2 children having type O blood. However, there are a number of different arrangements in which 2 out of the 5 children have type O blood. Specifically, there are 10 of them. Right, you can have the first 2, the first and the third, first and the fourth, first and the fifth, second and third, second and fourth, so on and so forth, right? We have 10 possible combinations that result in 2 of the 5 children having type O blood. All right? Each of these results in the same exact calculation. We have 0.25 squared and 0.75 to the third. We get this same probability of about 2.6%, or 0.02637. Right? So we know from previous work that when I want to know the probability of something occurring, I add up all the probabilities of how that thing can occur. So the probability of x equaling 2, or 2 children having type O blood, is 10 times the probability of 2 kids having type O blood, because there's 10 ways for that to happen. And we get 0.2637, about 26%. Right, is there anything I can clarify so far on this example? Okay, so we need a moment to write anything down. All right. Note, in the previous example, any one arrangement of 2 S's and 3 F's had the same probability. This is true because no matter what arrangement, we'd multiply together 0.25 twice and 0.75 3 times. We can generalize this for any setting in which we are interested in K successes in N trials. That is, the probability of X equaling K, probability of having K successes, is equal to, probability of exactly K successes in N trials is equal to the number of arrangements times probability of success to the kth power times 1 minus the probability of success, or the probability of failure, times N minus the number of successes. N is the number of trials. The number of ways of arranging K successes among N observations is given by the binomial coefficient, hence the name binomial distribution. We say N choose K. That's how that weird parenthesis that looks like it should be a fraction that's not written with a fraction line. N over K, we say N choose K equals N factorial divided by K factorial times N minus K factorial. Right, the exclamation mark is a factorial, and we have the description here on what that is. For K equals 0, 1, 2, up to N, right, where N factorial is defined as N times N minus 1 times N minus 2, so on and so forth, times 3 times 2 times 1. So essentially start at whatever that whole number is and multiply by each, successive minus 1 number. So if it's 5 factorial, 5 times 4 times 3 times 2 times 1. 10 factorial, 10 times 9 times 8 times 7 times 6, right? You count backwards, you multiply each of those numbers. That's how factorial works. We also have that 0 factorial is equal to 1, not 0. All right. We don't have time to get into why that is, but it's a thing. Does anyone need a moment to write this down? Right, what the binomial coefficient is. All right. We can also do this on our calculator, which you want to do. I can remember where it is. Yeah. I'll have to look that up and remind you guys later. I'm trying to remember where it is on the calculator and I can't remember. Because I use a different calculator all the time. All right, anyway, this can be done on your calculator. You do not have to do this all by hand. You use the NCR functionality on the calculator. So the binomial coefficient counts the number of different ways in which k successes can be arranged among n trials. The binomial probability p of x equals k is this count multiplied by the probability of any one specific arrangement of the k successes. Right, so we have the binomial probability formula here. If x has a binomial distribution with n trials of probability p of success on each trial, right, the possible values of x are 0, 1, 2 through n. If k is any one of these values, then we have the probability of x being exactly k equals n choose k times the probability of success to the kth power times the probability of failure to the n minus k power. Right? Make sure that this number plus this number, right, n minus k plus k, should equal n, the number of trials total. Right? If they don't, you've done something wrong. Right? Number of arrangements of k successes, the probability of k successes, probability of n minus k failures. Right? That's what each little part means. Right. How to find binomial probabilities. I'm sorry?
Could you go back?
Absolutely. There you are.
Thank you.
Mm-hmm. All right. Also, I found the button. So I'll take this opportunity real quick here. If you guys are on your graphing calculator, go to the math button, right? You don't have to hit second or anything before that. Click math. Click to the right so that you're highlighted on probability. And we have NCR here as the number 3 possibility. That's the choose function, right? Binomial coefficient function. So if we use that, it's actually selected something for me already. We can do 5. Oops. You have to put your number in there first. NCR 2, enter, 10 possibilities. Right, so the way to pick 2 successes out of 5 possible things, there's 10 ways. Right. So again, use math and the probability tab, and you get NCR. We won't get into NPR. All right, so I'm gonna switch on over to the next slide. So how to find the binomial probability. Step 1, state the distribution and the values of interest. Specify a binomial distribution with the number of trials n, success probability p, and the values of the variable clearly identified. All right, make sure that things you're using have been identified before you use them. That's a very important thing to do in math. Step 2, perform calculations. Show your work. Right, do one of the following. Use the binomial probability formula to find the desired probability, or use your calculator. Use binom PDF or binom CDF command and label each of the inputs. Right? If you're going to use these, what they mean by label each of the inputs, right? I'll show you in a moment here. Step 3, you've done your work, answer the question. All right. So in your calculator, you can have your calculator do a lot of this work for you. All right. The binom PDF command will find the binomial probability of exactly k successes. Binom CDF will find the probability of less than or equal to k successes. So if you need like 2 or fewer successes or less than 3 or something like that, you'll use binom CDF. Right? So in other words, each of these is slightly unique. I'll show you these on the calculator in just a second. This one, binom PDF, finds the probability of x equaling k. Binom CDF is the probability for x being less than or equal to k. So it depends on the context which one you would use. Right? In your graphing calculator, right, these can be found if you go to second and vars. Right above vars it says distributions. Go here. Right. It's a little bit faster if you click up. You'll see binom PDF, binom CDF. Up here is option A and B. Okay. Labeling each of the inputs means saying what number of trials, probability of success, and your value k that you're interested in, number of successes. Right. Those are each asked for as an input here. You say trials. Right. We'll use the example from previously. We have 5 trials, 5 kids. Probability of success is 0.25. Value of x we're interested in is 2. Right, so 2 successes. Remember, this is finding x equaling 2 successes. Enter and enter, and we get the same result as they had on the example. Right. So right here, what we see in parentheses, right, is what they're saying to label each of the inputs. So if you're going to use technology and you're going to use the binomial PDF function, you'll write n k, sorry, not k, sorry, np then k. This is what they would want you to write, right? That you showing that you use the calculator and you set it up properly, and you'd have your answer, right? So in our example, you would use binom PDF and you would write 5 trials, 0.25, and 2. And to be even more clear, it would be best to write it as n equals 5, p equals 0.25, and k equals 2. Right? This would be ideal if you're going to use technology and you want to show that, hey, I'm using technology to calculate this, I'm not doing it by hand, and this is what I put into my calculator. That's the expectation. Right? The same 3 values are used for binom CDF, but binom CDF finds that probability of having equal to or less than that number of successes. Okay. Is there any questions? Anything I can clarify? See, we need another moment to write anything down. Okay. All right, so examples. Again, each child of a particular pair of parents has probability 0.25 of having blood type O. Suppose the parents have 5 children. Right, find the probability that exactly 3 of the children have type O blood. Right. And if we want to, we can do this on our calculator. Right. I could even do second entry and just put a 3 in here and be done. Right. So we've used the binomial PDF entry here. It says it should be 0.08789, and so on. Let's see if they got the same result. So we're going to let x be the number of children with type O blood. We know that x has a binomial distribution n equals 5 and p equals 0.25. Right. And so p of x equaling 3 is the binomial coefficient 5 choose 3 times 0.25 to the third, 0.75 squared, and we get 0.08789, or about an 8.8% chance, which is the same as we got on the calculator. Right. Should the parents be surprised if more than 3 of their children have type O blood? All right, to answer this, we need to find the probability of x being greater than 3. Right, that's not a command on the calculator. We could use the complement rule if we wanted. They're doing this just saying, hey, well, we know we only have 2 more trials, right? To be greater than 3, that means we have 4 or 5 as possible outcomes. So they calculate probability of x equaling 4 plus probability of x equaling 5. That work is here, and they get the result of 0.01563, about a 1.5% chance of having more than 3 kids with type O blood. Pretty slim pickings. Right? Since there's only about a 1.5% chance that more than 3 children out of 5 would have type O blood, the parents should be surprised. And this is also an example of the type of question you might be asked to answer, right? Based on a probability, should an outcome be surprising? Should it be, is the statistic good or bad, right? There'll be questions like that. Is there anything I can clarify on these 2 examples? Does anyone need a moment to write anything down? Please raise your hand. The mean and standard deviation of a binomial distribution, right? We can describe the probability distribution of a binomial random variable just like any other distribution by looking at the shape, center, and spread. So the probability distribution of x equaling the number of children with type O blood in a family with 5 children. We get this probability distribution. Right? We can have values 0, 1, 2, 3, 4, or 5, each with those types of probabilities. Shape, the probability distribution of x is skewed to the right. It is more likely to have 0, 1, or 2 children with type O blood than a larger value. Okay. Center, the median number of children with type O blood is 1. Based on our formula for the mean, and again, they're using our basic mean formula for a random variable, right? Probability of an outcome times that outcome, add them all up, we get 1.25. Spread, the variance of x is, again, this same formula that we've used for random variables, right? We find the variance, and so the standard deviation of x is the square root of the variance, or 0.968. So we have these calculations, right? Luckily for binomial distributions, there's a shortcut to calculating the mean and standard deviation. We don't have to do all of this work unless we really want the practice. All right, so I'll show you that here. Does anyone need a moment to write anything down from this screen? Please raise your hand. So here's our shortcuts. Mean and standard deviation of a binomial or random variable. If a count x has a binomial distribution with number of trials n and probability of success p, the mean and standard deviation of x are n times p, right? And standard deviation is the square root of n times p times 1 minus p. So essentially, the number of trials times probability of success is the mean. The standard deviation is the square root of number of trials times probability of success times probability of failure. So that's kind of nifty. We don't have to do that massive calculation. If we don't want to, we can just do n times p and n times p times 1 minus p and take the square root. Pretty nice. Which also means np times 1 minus p is equal to the variance. Right, another shortcut. Please note, these formulas work only for binomial distributions. They can't be used for other distributions. These are special for binomial distributions, binomial random variables, and such, okay? Don't use them in other places. So we need a moment to write these down. Okay. So here we have an example. Mr. Bullard's 21 AP Stats students did the activity on page 340. Okay. This is about telling the difference between tap water and bottled water. If we assume the students in his class cannot tell tap water from bottled water, then each has a 1 in 3 chance of correctly identifying the different type of water by guessing. Right. Let X equal the number of students who correctly identify the cup containing the different type of water. All right, we're going to find the mean and standard deviation of X. Since X is a binomial random variable with parameters n equals 21 and p equals 1/3, we can use the formulas for the mean and standard deviation of a binomial random variable. All right, so we get the mean, mu of X, right, equals n times p, or 21 times 1/3. We get 7. Right, so this means we'd expect about 1/3 of his 21 students, about 7, to guess correctly, right? This is also assuming that their only way of getting it correct is by guessing, right? They can't actually tell the difference. We get the standard deviation of the square root of 21 times 1/3 times 2/3, and we get 2.16. So if the activity were repeated many times with groups of 21 students who were just guessing, the number of correct identifications would differ from 7 by an average of 2.16. All right. Is there any questions I can answer so far? Anything I can clarify? So we need a moment to write anything down from this slide. Binomial distributions are important in statistics when we wish to make inferences about the proportion P of successes in a population. Okay, so we're still using binomial distributions, but now we're talking about sampling. Almost all real-world sampling, such as taking a simple random sample from a population of interest, is done without replacement, right? Which means if we're looking at our traditional binomial distribution or binomial setting, that violates independence. Right? If I'm sampling without replacement, that means the probability of success is being reduced each time I pull someone, because there's less people in the population at that point to sample from. However, sampling without replacement leads to a violation of the independence condition, as I just said. When the population is much larger than the sample, a count of successes in an SRS of size n has approximately the binomial distribution, with n equal to the sample size and p equal to the proportion of success in the population. So essentially, if the population is way larger than the SRS I'm taking, or large enough, then I can still use a binomial distribution to approximate what's going on. Right. To check this, we use what's called the 10% condition. When taking an SRS of size n from a population of size capital N, right, we can use a binomial distribution to model the count of successes in the sample as long as the size of the SRS, right, the random sample, is less than or equal to 1/10 of the size of the population, or it's less than or equal to 10% of the population. Right? As long as it's smaller than that, we can use the binomial distribution. So we need a moment to write this down. Please raise your hand. So as n, all right, so normal approximations for binomial distributions, as n gets larger, something interesting happens to the shape of a binomial distribution. The figures below show histograms of binomial distributions for different values of n and p. What do we see as they get larger? So we have n of 10, p of 0.8. We have the same probability here, but now n is 20. Now we've moved our sample size up to 50, same probability. The shape goes from skewed to approximately normal. This is a good thing. This allows us to do more stuff. We can use a normal approximation for binomial distributions if it passes the large counts condition. All right, so this is a binomial distribution that is past the 10% condition that we can now check for the large counts condition to see if I can use a normal approximation to calculate probabilities. Suppose that X has the binomial distribution with n trials and success probability of P. When n is large, the distribution of X is approximately normal with mean and standard deviation. Mu of X, or mean of X, is NP. Standard deviation is square root of NP times 1 minus P. As a rule of thumb, we will use the normal approximation when n is so large that NP is greater than or equal to 10 and n times 1 minus P. Right, so it's not the entirety of this, it's just n times this. It's greater than or equal to 10. That is, the expected number of successes and failures are both at least 10. Right? If it passes this large counts condition, I can use the normal approximation. So you would need a moment to write this down. Please raise your hand. Right, unfortunately, there's not an example of that, but there is examples in the videos and things. The last setting we have here is a geometric setting. Right? In a binomial setting, the number of trials n is fixed, and the binomial random variable x counts the number of successes. In other situations, the goal is to repeat a chance behavior until a success occurs. These situations are called geometric settings. So in a geometric setting, the number of trials is not fixed, but what I want to achieve is a success. I want to know how long does it take to get the first success. All right. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. On each trial, the probability P of success must be the same. Oops. So this is a geometric setting. So if you're asked how long or how many trials do we expect it to take for the first success to occur, that's going to be geometric, as long as the probability of success is the same for each trial. So we need a moment to write this down. In a geometric setting, if we define the random variable y to be the number of trials needed to get the first success, then y is called a geometric random variable. Probability distribution of y is called a geometric distribution. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. Probability distribution of y is a geometric distribution with parameter p, probability of success on any trial. Possible values of y are 1, 2, 3, up to whatever, right? There's no real endpoint because the values of y determine how long it takes, which is not preset. Like binomial random variables, it is important to be able to distinguish situations in which the geometric distribution does and doesn't apply. Right? The key thing you're looking for is, are you being asked to determine how many trials it will take to get success? That's a big cue that you're looking at something that could be geometric. Okay. Can you raise your hand if you need a moment to write anything down? Okay. So here's an example. We have the lucky day game. All right, the context of this is that a teacher will typically give 10 homework problems. All right, as an alternative, the class can agree to play the lucky day game. The way this works is that a student is selected at random from the class and asked to pick a day of the week. Then the teacher uses technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will have only one homework problem. If the student picks wrong, teacher selects another random student who will choose another day, and the teacher will randomly then choose another day to be the lucky day. If the guess is correct, then the class will have two homework problems. The game continues until a student correctly guesses the lucky day. Your teacher will assign a number of homework problems that is equal to the total number of guesses made by the members of the class. All right, so in this case, we're interested in how many trials does it take to get a correct guess. This is a geometric situation. All right, the random variable of interest in this game is y, the number of guesses it takes to correctly match the lucky day. What's the probability the first student guesses correctly, right? We also do know that there's only 7 days to choose from, Monday through Sunday, or however you want to label that, right? So the probability of success is 1 out of 7. There's 1 correct answer, 6 incorrect answers, right? So we have a fixed probability. It's the same chance of getting a success on each trial, right? And so we have these probabilities we're interested in. Probability that it being the first guess, we have a 1 in 7 chance. Pretty straightforward. Probability that the second student guesses correctly, right? We have first one guesses wrong, second one is correct. We get 6/7 times 1/7, 0.1224. 3 guesses, that means 2 incorrect guesses in a row times a correct guess, get 0.1050. We can see how this builds itself up as we continue. The number of failures essentially continues to get higher, and so that number is multiplied by more, and we get only 1 multiplication by the success rate. So in general, we get this geometric probability formula. Right? If y has the geometric distribution with probability p of success on each trial, the possible values of y are 1, 2, 3, all the way up to whenever it occurs. If k is any one of these values, then the probability of y equaling k equals probability of failure 1 minus p times k to the k minus 1 power times the probability of success. Okay. So this is our formula. There's just kind of nice. It's a very simple formula. Okay. See, we need a moment to write this down. for your notes. All right, so calculating the mean of a geometric random variable, the table below shows part of the probability distribution of y. We can't show the entire distribution because the number of trials it takes to get the first success could be an incredibly large number, right? We show up to like 26 trials, but obviously it could take longer. You could have really bad luck, so to say. All right, so we have a probability distribution, part of the probability distribution here in table form. The 3 dots mean that this continues. Again, it could be infinitely long. We're not going to try and show them all. All right, our shape, the heavily right-skewed shape is characteristic of any geometric distribution. That's because the most likely value is 1. Right, probability that the first guess or the first thing is correct or success is the highest probability. Center, the mean of y is about 7. We'd expect it to take 7 guesses to get our first success, right? There's 7 days in the week. We would assume that on average, it should take it about 7 guesses to get one right. Spread, the standard deviation of y is 6.48. If the class played the Lucky Day game many times, the number of homework problems the students receive would differ from 7 by an average of 6.48. It's kind of a big swing. Right, so we get the mean or expected value of a geometric random variable. Right? If y is a geometric random variable with probability p of success on each trial, then its mean or expected value is 1 divided by p. Right? Fairly straightforward. Right? It's about as basic as it gets. 1 divided by the probability of success. Right? In this situation, right, the probability of success is 1 over 7, or 1/7. 1 divided by 1/7 is 7. Right? Also, on your calculator, if we go to the same second vars to go to our distribution tab, we have Geomet PDF and Geomet CDF, similar context to the binomial PDF and binomial CDF. The PDF is x equaling a specific value, right? So what's the probability of it taking exactly 4 trials to get the first success? The CDF says less than or equal to a specific number of trials. So what's the probability of it taking less than or equal to 5 trials to get a success? Right, so we have these 2 functions. These use the same parameters as we would expect it to use. You have your probability of success and number of guesses to get that first success. Right, so this only has 2 conditions. Remember, we don't have a condition of n like we would in binomial because we don't have a fixed number of trials. And this works the same. Right, so we do have those in your calculator as well, which is kind of nice. Is there any questions or anything I can clarify? All right. So then, that is the lesson. We covered binomial and geometric and random variables. Right, and there's special conditions for using binomial and random variable. Right, that's checking your bins. We can compute and interpret probabilities involving binomial distributions. Right, we can find the mean and standard deviation of a binomial and random variable and say what they mean. Find probabilities involving geometric random variables, and when appropriate, use the normal approximation. Right? This is not covered in this slide, they didn't do the example, right? But when we have that 10% condition and the large counts condition satisfied, we can use a normal approximation along with a binomial distribution to find probabilities. And we've reached the end of the slides. All right. Are there any questions, or is there anything I can clarify or go over or show an example of to help better your understanding of what we just saw? All right. So with that, this is the only day that I get to see you guys for content this week. So it does make it a little tough. I do recommend trying the practice problems for section 6.3. The solutions are obviously provided in Canvas. See if you can make sense of those, see if you can get to some answers, see if you have questions about them. I have the assessments for chapter 6 set as due just because we finished the chapter this week. On Friday. Please don't feel like you need to finish them by Friday. It's just to make sure that they're due before we start chapter 7 next week. All right. We will be starting chapter 7 next week. Yes, Caesar, you have your hand up? Or it looks like you have your hand up on one of my screens.
Sorry, I've put it down.
Okay, that's fine. It was showing up on one of my screens, but not on the other screen. That's why I was like, confused. But it's okay. You should hopefully be able to start the assessments for chapter 6 either by the end of this week or next week, because we will be moving into chapter 7 next week. I will be making available a Desmos activity to help practice some of the stuff from this section. It will not be assigned, but I will be using it in my Thursday, Friday period 2 class, because they do get me for 2 days. So I have that for their second day. So I will make it available for you guys to have another resource to practice with. Okay. Is there any questions? All right, well then with that, that's all we have for today. If anything comes up, if you have any questions, you need clarification, please let me know. Email me, send me a message somehow. I will be happy to help. All right, have a lovely rest of your week, and I will see you next week.